So let's move on to our final presentation, case study to look through today, and that is aquatic centres. And we've got Brendan joining us from Bridgeford Group. But before he does, let me just give you a little bit of context on aquatic centres. There's some 200 reasonable size aquatic centres, maybe up to 400 or so if you include swim schools within Victoria. Some 3 or so petajoules worth of gas usage down there. So this is a really big issue and big opportunity for Victoria to reduce gas and to decarbonise. Heat pumps are well used in the warmer states, certainly from New South Wales up, very commonly used, but not so commonly used in Victoria and Tasmania and all South Australia. In the past, low gas prices have encouraged the usage of CHP or combined heating and power systems, basically a big gas engine. But now with high gas prices, that is not looking like a great option. And combine that with what is seen as very high maintenance costs is not seen as a great option with those gas engines. So people are certainly looking to get away. You've got local councils who want to get away from gas and decarbonise. So you've got plenty of momentum there. What we also see affecting the market is this, I'll say, next generation of aquatic centre heat pumps where they use low charge ammonia. That's the LCA, low charge ammonia heat pumps. And we see that's perfectly matched to the demands of what an aquatic centre needs in terms of its heating requirements. From that, you can get very high COP, very good industrial grade equipment and really good efficiency overall. And so we see this being a big part of that going forward, as well as implementing better heat recovery and better building insulation as well. We know that a lot of aquatic centres have been designed to look nice and have lots of glass, but a very poor thermal performance. So lots of potential here. And so we thought we'd explore this further. And so joining us today, we have Brendan Vos, and I'm not sure if Nick made it. Nick was a little bit of a question if you'd make it there, but we definitely have Brendan Vos online, the director for Bridgeford Group, who has worked very closely with these aquatic centre upgrades. And Brendan, I'll ask you to come and share your screen and take us through the projects that you've been looking at. Stop sharing of mine. Yep. Brendan, that's come through, but I can't hear you as yet. Maybe a mute going on there.
Unmute, and I'm going to put my video on, start video. Okay, the host has stopped my video, but aside from that, we're all good. So, cool. So firstly, just want to say thanks to A2EP and everyone for having the opportunity to present. It's really great to see so many people online and some really cool case studies. So thank you. I joined Bridgeford Group in October last year after spending 9 years with Smart Chiller Group. So see a few familiar faces in the audience list. So yeah, good to see that. Since I joined Bridgeford Group, I've been really fortunate to be part of multiple energy transition projects, predominantly focused in asset electrification, particularly just gas assets in commercial buildings. Let me just make sure this slide is going this way. So I'll just give you a bit about Bridgeford Group. So we work primarily in the retrofit space. We focus on practicality as part of what is a much bigger integrated energy and infrastructure picture. So since October, we've worked on now over 120 buildings, 150 buildings in facilities such as universities, office buildings, aquatic centres, many others. All these projects have ranged from roadmaps to feasibilities to detailed engineering designs, which has been really good to be part of. One of these projects is actually Kardinia Aquatic Centre, which was initially done as a concept in August 2021. It's just a feasibility study to help inform the City of Geelong on their electrification pathways. This project's now in detailed design, so it'll be good to walk you through some of that as well. As we know, retrofits are typically bound by a lot of constraints. We've heard some of those today, space, power being the two primary ones for electrification. This project had a little bit of everything, including an integration into what is a wider net zero emissions pathway for the City of Geelong. And we are lucky enough to have Stephen Rodwell on from City of Geelong today in the background if there are any questions to do with what that wider context and net zero emissions pathway looks like for them. So being that I wasn't here when we first did this concept, I'll hand over to Nick, who's our managing director, who'll walk you through the project itself. So,
great. Thanks, Brendan. And thanks for having us on the line here. Brendan will be controlling the screen as well, so I'll have to remind him to click next. So the site in question is Kardinia Aquatic, so it is right near the cattery down there in Geelong, and worked quite well for Brendan as he is a Geelong supporter. I'm a doggies man, so felt like going to enemy territory down there. So in terms of the project overview, what prompted this project? Firstly, Geelong have a net zero target 2025 for own operations, and one of the existing boilers was coming to end of life, and that then presents a key opportunity to electrify the site. They also, during COVID, I believe one of the councils had promised that the centre would change from seasonal use, I think from November to March, to all year round, or maybe it was October to March, all year round. And that presented challenges in terms of, could the existing plant or the new electrified plant cope with that increased operation? So the opportunity here is, how can we maximise the emissions reductions to net zero via electrification? And I suppose that's within the constraints of the facility itself, which we talked a bit about with the other case studies today. Brendan, I'll get you to go to the next slide. So just a bit of an overview of the site. 6 pools there: FINA pool, Olympic pool. So they're your large pools. It is an outdoor aquatic centre. Diving, water slide, learner and toddler. And they are serviced by a centralised plant with 2, I believe, 800 kilowatt boilers there. And the site has existing electrical constraints, which is not uncommon for aquatic centres. And I believe the transformers, I think it was 500 kVA or 315 kVA. So it does present challenges with electrification. High existing gas consumption, being an outdoor facility. The requirement to make sure that we have not only the reduction in energy, but also providing the load that's needed. Geelong purchased their electricity from VECO, the Victorian Energy Collaboration, meaning that it is zero emissions electricity. So it does present as a great opportunity to go from natural gas to electrified hot water. From an operational perspective, the change in operation from seasonal to year-round proposed some challenges. Various water temperatures as well across the system. Some pools operating with covers, some without. Next slide there. So something that we focused on, particularly the concept phase, was to say, well, what will it look like to fully electrify the system, and is there a partial solution that might work given the site constraints and, I suppose, the diminishing returns as you fully electrify. We developed a calibrated pool simulation model to determine the optimised heat pump sizing and provide the financial benefits of electrifying. This model included directional wind speed, sources of heat gain or loss, including evaporation, conduction, radiation, ability to convert from seasonal to year-round, calibrated against actual energy consumption, as well as local weather data, temperature, relative humidity. By doing this, we were able to see the alignment between the operation of the current equipment sizing and model. So our model wasn't saying we needed 3,000 kilowatts, but it was fairly close to the 1,600 was there. The year-round operation didn't mean there may have been a small change required into the capacity, but not drastic. And then alignment to the baseline energy data. Now, given the pool load was driven by evaporation, wind speed, or ambient temperature, humidity, this model produced some interesting results. And what we can see here with that heat load distribution is that 45% of the year, the load is under 400 kilowatts and under a megawatt for 80% of the year. So what we actually looked at was partial electrification to provide the best bang for buck from an emissions reduction opportunity. Next slide, Brendan. So we presented a number of options here, which is shown on this slide. So what the current system was to operate, including offsetting of those gas emissions, a boiler upgrade only, heat pump at a 400 kilowatt and 800 kilowatt, and then fully electrified. And you can see there's a drastic uplift in payback for the fully electrified solution because of the need to upgrade the transformer and incoming feed and all the electrical infrastructure, while the partial electrification option can sit within the current electrical confines of the site. Something that we do focus on here as well as marginal uplift. As one of the boilers is at end of life and will be replaced anyway as part of that sort of maintenance upgrade budget, we looked at what the cost uplift was to electrify from the business as usual case there, and then what the payback on that uplift be. As you can see here, some pretty attractive figures here because of the high hours of operation proposed for those heat pumps that aren't sitting at peak load. Next slide, Brendan. So we've got a few key takeaways here, and we're terming this sort of operation-led design. And by sizing for partial electrification, you can put in a heat pump that doesn't fully electrify the sites, but it's sizing it for, let's say, half capacity, 800 kilowatt instead of 1600. You actually get close to 90% of the emissions reduction because you're having those heat pumps run so many hours in the year, and the pools themselves are a bit like thermal storage tanks. And if you think that you may have a fixed budget to spend on electrification, you can either spend it all at one aquatic centre and fully electrify, or you could spend it across 2 aquatic centres, and you have the potential to get up to 1.8 times the emission reduction combined between the 2 aquatic centres than one. And that's some of the thinking that we've employed here to say, well, at some point you want to fully electrify, but to get the best bang for buck now and the most emissions reduction today, actually do partial electrification at one and partial electrification at the other, and then come back around and fully electrify those aquatic centres later. I think that's a bit of an interesting way of thinking about this, rather than just looking at it with one facility in mind. As I mentioned, that focus on marginal uplift and savings compared to BAU asset replacement assists in payback. Otherwise, you've seen these paybacks look quite high, but you're not capturing that either avoided capital cost or that business as usual upgrade should occur. And with that, the partial electrification designed within the constraints of end-of-life electrical infrastructure, pool operation and load. We weren't too spatially constrained on this one, which is lucky. But some of the other aquatic centres we're working on, which are in more urban settings, have a lot of spatial constraints there. Other opportunities and considerations, as mentioned, the pools do act as thermal storage systems for the heat pumps. So you have the ability as well to float set point, particularly if there's a high requirement for peak load, but that might only occur in 1% of the year. If you're okay with the temperature in the pool floating lower during those periods, you can size the heat pump smaller again. The addition of or regular use of blankets will drastically reduce that energy consumption. If you can cover it when you're not using it, it's fantastic. The other thing that was very interesting is the wind speed. And there was a graph with the load duration curve a few slides back that showed the effect of wind speed to evaporation loss. And something you don't see a lot of, but can be actually a really good energy saving measure, is looking at wind breaks around the pools to stop that high wind speed directly over the pool surface, contributing to evaporation. The benefit for Kardinia was we have the stadium right there, which does help somewhat with the wind over the pool. And I think that may be pretty much everything. Brendan, do you have anything else that you would like to add to that?
No, so just obviously all of those key takeaways are applicable in all the other aquatic centres. I think that we've dealt with. Some are, one we just spoke to is looking at one outdoor pool and a combination of indoor pools, and we've looked at some indoor aquatic centres. Obviously, wind velocity, a bit less of a problem in an indoor aquatic centre, but you get a bit more of a spatial constraint. So each one of these we've looked at has been integrated into a wider net zero emissions picture or a pathway for a client. We're lucky that our clients are looking at it from that perspective, and we're glad that we can help them on that journey. So that's it.
Fantastic, and really inspirational way to look at those problems and solve them, thinking outside the box there and thinking forward. Stephen, any comments, observations there? It sounds like you guys are on a great journey.
Yeah, I think it's from a council perspective, it's great that there's people willing to share their expertise and guide us along the journey. We're looking at 21 sites with varying levels of gas to electric conversion involved. So it's pretty confronting, and there's a million variables. But yeah, certainly it's a great community, I think, out there, and I see a few names in the attendees who have certainly helped us on our journey. So great to share the information and move forward with this.
Brilliant. Wish you all the luck. And that electrical transformer upgrade, we've seen that in other cases where that really does blow the case right out of the water. You know, a couple of solar panels on the stadium next door and behind the meter, and boom. But I don't want to tell you how to. Good one. Hey, Ahmad, are you there? Let's have a quick look at how there's some of those key issues and how that affected, and so we'll see those in the guidelines as well. If you just we'll try it for 1 or 2 minutes once again. Hey, Ahmad.
Yeah, sure. It is very exciting to see that actually the actual experience out there is supporting the arguments that we have been making in the guidance document. For example, Nick spoke about the heat loss from the surface of the water because of evaporation from there and the impact of wind speed. We have brought many of those items, including that one, under the heading of energy efficiency in an aquatic centre. And for outdoor pool, it is probably a little bit more challenging. For indoor pools, we discussed how, for example, increasing relative humidity in an aquatic centre can reduce evaporative heat loss from that surface. Then we talk about water temperature there, and in many cases throughout this work, we have emphasized that heat pumps are not one-to-one swap. You do not need to stick with the existing design. For example, for water temperature, when you are switching to heat pump, you can revisit that, reduce that temperature if it is possible. Load smoothing, very, very interesting to hear you guys talk about the utilization of the pool itself as a thermal storage. That's a massive amount of water in there with huge thermal loss, and it can help to smoothen the load there by, for example, slightly increasing the temperature of that body of water, and it can be actually like an intraday sort of intra and intraday sort of thermal storage. Lots of opportunities for waste heat recovery in an aquatic centre. We have spoken about them in the guide. One of the important things is that there is a huge amount of latent heat in the exhaust air from aquatic centres. At least several analyses have shown that at least 50% of that heat loss due to evaporation from the surface of the water can be captured by heat pumps because they are able to condense that moisture of that air and capture its latent heat. You spoke about a space constraint. It is, as you said, it is sometimes an issue there, sometimes it is not, but it is still there, and we need to consider that. And very interesting to hear from you guys that auxiliary heating, how you are approaching that. We have mentioned a backup heating in our document. It is similar to the idea you guys explained here by saying that we go with 80% electrification and still use, for example, other sort of heating technologies for 20% of the time. If you look at air procurement, probably the most important thing we have highlighted there is that the heat pump needs to be industrial grade sort of heat pump, being able to resistant to corrosion, high on time, low maintenance, a very reliable sort of heat pump. So I do not waste the time now by reading through those items. I stop here in terms of that. Just one more thing, Jarrod, I mentioned here, and then I stop. Just a very rough estimate of the benefits that one facility can gain from the DEU program. It has been put into the small table there by replacing 30,000 gigajoule of heating requirement from a gas boiler with 85% efficiency, switching that to a heat pump that has a COP of 4. Almost 1,000 weeks can be secured for that, and its net revenue at the current price of these weeks is estimated to be around $60,000.
Brilliant, many thanks, Ahmad. And yeah, we do see that VEECS being an excellent assistance for aquatic centres. That 30,000 gigajoules per annum is really quite a common amount, somewhere around there. Some use more, some less, of course, but you know, that's quite an amount of revenue that can offset that that investment in the heat pump. So good to see that support there. Wonderful.